So we're going to start into our new unit of freely falling objects, or objects that are in free fall. And this is our continuation of kinematics, just now dealing with motion along the vertical axis. So here we go. All objects dropped near the Earth's surface fall with the same constant acceleration in the absence of air resistance. It is very important to understand that this is in the absence of air resistance. So the force that is responsible for that air resistance we do not take into account right now. We will bring it back in when we're ready to talk about forces. So for right now, no air resistance. Therefore, all objects are going to fall at the same rate of acceleration. I'm not normally a huge history of physics person, just because I think a lot of times when we learn something new, it kind of replaces our understanding of what we have. But in this case, I think it's a worthwhile discussion. Okay. Aristotle, as you can see by the dates, believed a long time ago that heavier objects fell faster than lighter objects. And that was an accepted way of understanding how things fell. However, the fact was was disputed a little bit later, okay, when Galileo conducted some experiments with balls on an inclined plane. And effectively, here's what Galileo did. He took two different massed spheres, set them at the top of an inclined surface, from rest, released them, and observed how long it took for them to get to the bottom of the inclined plane. And what he realized was that those objects, those spheres of different masses, were able to get to the bottom of this inclined surface at the same time. And then he took it one step further. Well, what if that inclined surface was then made to be vertical? Okay, so two different spherical objects of different masses then were effectively released from rest, and we observed, and he observed, that they reached the ground at exactly the same time. So we could use some of our kinematic equations to go ahead and describe the motion of those objects as they're rolling down the inclined surface. But what I want to do is to take a moment and actually show you a video clip of something, well, a couple of years ago, August 2nd, 1971, an astronaut named David Scott did a gravitational experiment on the moon. Now, obviously, doing an experiment on the moon provides for a unique situation. Why? There's no air resistance that we're going to have in the moon because there's no atmosphere. So let's just take a quick look as to what was discovered or confirmed on the surface of the moon.
Well, in my left hand I have a feather. In my right hand a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
I love the, so how about that? So obviously we have those hammer and the feather dropped when on the moon, where the gravitational field is a little different than it is here on Earth. So it doesn't fall at the same rate that it would here on Earth, but they're both able to fall at the same rate relative to each other. There's no atmosphere there, no particulate matter to slow that down on its descent. So they fall at the exact same rate. Okay. So let's go ahead and put it together formally. I know there's a lot of stuff here on this slide, but by definition, a freely falling object is any object moving freely under the influence of gravity alone, meaning that there's nothing else pushing it or pulling it as it's going down. And that is regardless of its initial motion. So an object that is thrown upwards, or an object that is thrown downwards, and those released from rest, can all be considered to be in free fall once they are released, assuming that there is no air resistance or nothing else pushing or pulling it. Okay, this last statement here at the end is very, very important. Any freely falling object experiences an acceleration directed downward regardless of its initial motion. An object that is thrown upwards, while it's rising, the acceleration is still going to be directed downward. Okay? As it falls back down, it's still going to be directed downward. Now, earlier in our formative, we had talked about the value of g. We had seen in our data tables that we no longer have a in our data tables. It's replaced with the lowercase letter g. That value of g stands for the acceleration due to gravity. It is not just simply gravity, because there's actually two different things, and a lot of people that don't really know a lot about physics just simply state gravity. There is a gravitational force, which we're not really prepared to talk all about just yet. There's a gravitational force, and there is the acceleration due to gravity. And this value of g stands for the acceleration due to gravity. Technically, this acceleration due to gravity does change with increasing altitude. Okay, we will talk about that a little bit more in Newton's universal law of gravitation, but just to give you a quick example of this, if you were to do some gravitationally based experimentation and do that at the top of Mount Everest and at the bottom of Death Valley, okay, we have a difference in altitude there. You would find a very small difference in the acceleration due to gravity because of that altitude. Effectively, the lower the altitude you are, the greater that acceleration due to gravity is going to be. The further away you get, the less it's going to be. Now, at the Earth's surface, and in terms of this course, all of the discussions we're going to have so far, we're going to assume that the acceleration due to gravity is going to be negative 9.8 meters per second squared. Okay? Technically, it's negative 9.801, and it keeps going beyond that at the surface of our Earth. And again, it does vary slightly depending on your altitude, but for all the examples, we're going to make an assumption that that acceleration is going to be negative 9.8 meters per second squared. Okay, just a couple of quick images, and one of the things I want for us to kind of get out of this is to maybe understand some of the different types of trajectories we can have in free fall situations. So in this example that we see here, we're going to drop an object from rest. Okay, in this example, kind of wish that they would use the negatives that really should be in here. But if we were to release an object from rest, that's going to start at a velocity of 0 meters per second. After 1 second of being in free fall, the velocity would be negative 9.8 meters per second, 2 seconds, negative 19.6, 3 seconds, negative 29.4. Now, all of this is assuming it doesn't hit the ground. So if it were to only fall for 1.5 seconds before it hits the ground, well, we're not going to get to 2 seconds, we're not going to get to 3 seconds. The only time it would be accelerating due to gravity is from when it is released until the moment when it strikes the ground. Now, depending on your example, you could have something that falls for greater than 3 seconds. Just this is what's provided in this image. So that's one type of trajectory, we can call it, I guess, about an object that's simply going to be released from rest. Another kind is, what happens if we throw an object up into the air and it returns back to the same height? We will call this a symmetrical trajectory. So in symmetrical trajectories, one of the things I would like for you to notice is take a look at what the speeds are at the same height. So if this guy throws up this ball up into the air with the initial velocity given, and it returns back to the exact same height, notice positive 19.6 upon release. When it comes back to the exact same height, the velocity will be negative 19.6. The negative just meaning the direction, so the speed is exactly the same. Okay? One other thing to notice, anytime we go up to a maximum height at that point, as a very finite point, the velocity at that point is going to be 0. It doesn't go up there, hang out for a little bit, and then come back down. Okay, but there is a point that it gets to at the maximum height. At that point, that is a velocity of 0. And that's very important if we're going to do some calculation to find what that maximum height is going to be. Okay. One more thing I also want to say about this. We could have a problem where, let's say this guy throws this object up, maybe it doesn't return back to the same height, and let's say maybe it hits the ground. Okay? Well, if that's the case, we would consider that to be what we call an asymmetrical problem, where It does not take the same amount of time to go up as it does down because it's going to a different height than where it started. And we can see a couple of different examples of that. One more slide here on our notes, and that's taking a look at the kinematic equations for free fall. Okay, and what we will notice is these are the same three equations that we had previously in our horizontal motion. We certainly see that the A for acceleration has turned into G for the acceleration due to gravity. We also see delta X has become delta Y. There is some notation here, though, that's kind of new for us that I want for us to be able to see. We see Vy final and Vy initial in several of these equations. It still stands for V final and V initial, but we're now needing to separate what's happening between what's going on our vertical axis, on our y-axis, versus what's happening along our x-axis. So technically in our last unit we should have also had Vxi and Vxf. And most of the reason why I want to introduce this to you now is because our next unit, when we get to two-dimensional motion, we're going to have to separate our vertical and horizontal data. So we're going to kind of use these subscripts a little bit more. So, for example, though, this first kinematic equation that's listed here, it's still going to be V final equals V initial plus GT. You can still write it that way. I just need for us to start to be able to get used to the notation of Vy final and Vy initial. One other thing, you'll notice that there is not an equivalent equation of delta X equals 1/2 Vi plus Vf all times t, mostly because that equation does not have the acceleration due to gravity